Hi, this is David Pepper with my 3-minute narration of my poster. I'm looking at the GAN game from the standpoint of a game theorist. So the first panel gives the flow of the game, the player's strategies and outcomes that define the game. One thing that's important to note is that given the utility functions that we use, this is not a zero-sum game, although it's commonly reported to be such. That is, there are times when changing one player's strategies can make both players better off. That's never true with the generator, but sometimes the discriminator can adjust their strategy in such a way that both the discriminator and the generator are better off, at least for a portion of the time, and that's shown in the bottom figure there. So there are some ranges where it's a positive sum game, and that is not necessarily bad. There's many positive sum games that we like to look at. To understand this game, and use a technique that we use in applied game theory, which is to create a toy version of it, a simple version of it that is hopefully complex enough to capture the basic elements of the model, so that understanding this model will help us understand GANs out in the wild. So this is a game called the distribution matching game, where there's just 3 boxes, A, B, C, and the strategy for nature is every turn, with probability theta A, it chooses A, theta B, it chooses B, and theta C, or 1 minus theta A minus theta B, it gives a C. So there's some probability distribution over those. The generator has its own version of that distribution, PA, PB, PC, down at the bottom. And then the discriminator has strategy QA, QB, QC. So QA will be, if it sees A, what's the probability that it thinks that that is from nature as opposed to the generator. Same thing with QB and QC. So its strategy is a 3-dimensional object in this version. All right, so it sounds very simple. We can initialize everything randomly. Question is it sophisticated enough to actually capture what happens in GANs? And the answer is yes. That for different parameter values on learning and so on, as you can see at the bottom of the page, we can recreate problems with cycling, with non-convergence due to overlearning, to mode collapse, and non-convergence due to underlearning. So actually we can have this do all the things that a GAN does. Now the question is how to clean it up. One is to use only rationalizable strategies. In game theory, that means that there's some beliefs that make your actions rational. That's not necessarily true for D having QA, QB, QC here. Those aren't necessarily consistent with Bayes' rule. And this surface here shows the subset of rationalizable strategies for D in the subspace of all strategies. The other is that in training, what happens is that the discriminator tries to follow actually nature, but then the generator follows the discriminator, and in fact it tries to follow what the discriminator thinks nature is at that moment. So in fact, the generator is kind of pulling the discriminator along. These insights say that we should be training using belief space, not action space, and that we should incorporate the delta in D's movement every time into the generator strategy. Thanks very much.